Hey guys, welcome to secondary chemistry. Today we are going to look at the topic of Brownian motion. Before we start, we have to talk about the idea of particles, more specifically about the concept that all the substances around us consist of something like smallest particles. Even long ago, a Greek philosopher called Democritus found out that every substance, some harder, some easier, can be divided into smaller pieces. For instance, you could take a piece of paper and cut it into smaller pieces over and over again, and theoretically at some point you would find that you cannot divide the piece of paper any longer, and then you would remain with the smallest particle of the piece of paper. So all the substances around us consist of smallest particles, which in sum build up matter. And we imagine those particles to be spherical, and particles of different substances, they differ in mass and size. Let's illustrate this. For example, if you have an aluminium block, then we imagine this aluminium block to be composed of plenty little tiny aluminium particles. And the substance wood consists of many wood particles, but wood particles are not the same as aluminium particles. They have a different mass and a different size. And another important thing is that particles are held together by attraction forces. This means, for example, that within aluminium, the particles attract each other. They attract their neighboring particles, just the particles around them. And this is the reason why substances are actually stable. Maybe you're sitting at a table, and the reason why the table is not falling apart is that there are attraction forces between the wood particles within the table. Now we have heard something about the idea that all the substances around us are composed of little particles, but we don't really know something about the nature of these particles. For example, the question whether these particles are stationary or if they are moving. Of course, we can't see particles move because they are too small to see them, but still, theoretically, they could be moving all the time. And an experiment will help us to find out, something about the nature of the particles. There's a quite nice experiment concerning this question. And what you can see here are two colorless solutions, one iron solution in the dropper and a thiocyanate solution in the test tube. As mentioned earlier, both solutions are colorless, but if you mix them and if you drop something of the iron solution into the thiocyanate solution, you can see this nice red color which looks blood-like, and that's why these two chemicals are used to make fake blood in movies and theater and stuff like this. If you want to do this, you put one colorless solution on a knife, which is not sharp, of course, and the other solution on your arm. And if you bring the knife in contact with your arm, then the red color, the fake blood, is running over your arm. Quite nice. But this means that we can use these two chemicals to have sort of an indicator to show us when particles of the iron solution mix or meet with particles of the thiocyanate solution. Let's have a look at a short experiment. Here we have a microscopic slide, and using a dropper we put a few drops of water, simply distilled water, and after this we add a drop of thiocyanate solution to the right end. Here you can see the colorless thiocyanate solution. And on the other end of this water film, we put a drop of iron solution with iron particles, also colorless as you can see. And now we leave this experiment just to stay. There's not even wind, there are no influence factors, simply nothing, and we start the stopwatch and wait and observe what's happening. And after a few minutes, round about 7 minutes, we can see a change. You can see red color occurring somewhere in the middle. Red color is visible, and if you leave this spot a little while longer, that red color becomes stronger and stronger. And this observation is quite interesting because it tells us something about the particles. The iron particles and the thiocyanate particles, because we know that this red color only occurs if particles from the iron solution mix and meet with the particles from the thiocyanate solution. But the thiocyanate solution we have put on the right and the iron solution on the left. Now, if we have red color in the middle, this means that particles from both solutions must have met in the middle. But in order to meet in the middle, they must have traveled from the left end and the right end. And for this reason, we have an evidence that even though we can't see it, the particles apparently must have been moving. So the particles move. And this is what Brownian motion is all about. Brownian motion states that particles are in constant motion. There are no particles in this universe which are not moving. Now we look at the effect of temperature on the particle movement. Again, you can see the setup of our experiment, the microscopic slide, the water film, and the drop of thiocyanate solution, the drop of iron solution, and the red spot in the middle. If you carry out this experiment with cold water, then the red color appears after around about 7 minutes. That's what you saw in the movie. If you instead use hot water on the microscopic slide, then the red color can already be seen after 2 minutes. What does that tell you about the particle movement? Well, if the red color appears earlier with hot water, we can conclude that particles travel faster or move faster at higher temperatures. And this is a very important thing in particle theory, that particles move faster at higher temperatures. And similarly, it's also true that particles move slower at lower temperatures. Let's wrap it up, the topic of Brownian motion. Brownian motion states that particles are in constant motion. Why is the phenomenon of Brownian motion called Brownian motion? This is because of the scientist Robert Brown. Here you can see a picture of him. He was a scientist and found out first about Brownian motion. He didn't use fake blood to see that particles are always moving, but he had a pollen grain within some water that he looked at through the microscope, and he observed that the pollen grain was jiggling and moving a little bit. And the pollen grain itself is composed of many, many particles, so it's too heavy to move by its own, but it was moving because the water particles were just dumping into the pollen grain and make it move. This was the conclusion drawn from Robert Brown to have another evidence to see that particles are always moving. So this is the takeaway from that topic. Brownian motion states that particles are in constant motion, and you can also remember that those particles are traveling faster when it is hotter. Thanks for watching, and see you in the next video.